Okay, last round. So let us finish what we discussed yesterday. So the open question which we still have to answer is, how is the gravitational field for a gravitational wave in this approximation we are doing? How is a gravitational field related to the source, and to what properties of the source is it related? And what we want to show is that to leading order in the far field, in lowest non-trivial approximation for the far field, that it is the quadrupole moment, the time derivative of the quadrupole moment that matters. So the situation we are considering was that we have a sphere of radius kr, and only inside the sphere is t mu nu different from 0. So the source, whatever it may be, is confined to this sphere. So we had this vector r prime, which we use as the integration variable. This ranges over the interior of this sphere where the field is possibly different from 0. And the observer is far away from this. He is at a position r, far away from this region. So he's in the vacuum region. And we want to know what is he measuring? What property of the source can he observe when he is far away from the source? And the equation we have to consider are, of course, the field equation. And we are working in the Hilbert gauge, so we have this here. And we had observed, I think this was the last thing I did last time, was that these two equations imply this conservation law, which is quite obvious, right? If you apply the differential operator d mu to this equation and you commute it with the box operators, then you have this result. So that's the usual conservation law from special relativity. This holds in this approximation here for gravitational waves. And well, then you have written one solution to this equation. This is the solution which is relevant for the case that no radiation comes in from infinity. That's the analog of the retarded potential in electrodynamics. And then we have expanded this in the far field. So in the far field approximation, this means that the length of this vector, the r prime, in comparison to this vector, is very small. Yeah? So remember, we made a Taylor expansion of a square root, and we took only the leading order term, and we neglected everything else. And what we got was then the following expression for the gamma mu nu in the far field. What's the factor? Kappa over 2 pi. So this is gamma mu nu at time t and position r, here, there where the observer is. And that's an integral over kr, of course, with a prefactor kappa over 2 pi r. And under the integral, we have the energy momentum tensor. We can write it with upper or lower indices, doesn't matter. At a time which is retarded by the time a light ray needs in order to travel from here to here. And the integration variable is r prime. So the volume element is written with respect to the prime coordinates. And what I want to show is that in this approximation, I think I had written it with the upper indices, and that's actually the expression we will need in the following. In this approximation, we will see that this expression is given by the second derivative of the quadrupole moment, and that's what we have to calculate now. So the quadrupole moment, this has only spatial indices, qkl, and it depends on t. And what's the integral? Yes, over the region where the energy momentum tensor is different from 0, too at time t and position r, xk, xl, dv. So r is a vector with components x1, x2, x3. K and l takes values 1, 2, 3. By the way, the position of the indices is irrelevant, right? So if I have this expression, I can pull one index down. This gives a minus sign, right? Because eta naught naught is 0, is minus 1. And if I pull the second index also down, then I get plus. So here you can really identify this with the energy density, which is a quantity with lower indices, right? So this is the energy density. Okay, and now we have to calculate. So from the quadrupole moment, I calculate the time derivative. And then I calculate the second time derivative, and then we compare with this expression. And if I've done everything correctly, then we should get the result that the two things are equal, up to a factor. So what is this? So d by dt means I differentiate with respect to the coordinate x0, which is c times t, and then I have to multiply with c, right? So d by d naught is 1 over c d by dt. So this is the time derivative. I have to write a partial integral, partial differential under the integral because the function depends on several variables. Outside of the integral, it is a total derivative, right? Because the whole integral depends only on t. The r is integrated away. So I get this expression here. Tr xkxl dv. And now I use this property here. I use the fact that the divergence, which is built with partial derivatives, is 0. So I can, c is of course a constant. I can write this as minus di, tio. Yeah? I takes values 1, 2, 3. So this term together with this here, with a plus sign, both terms give 0. So they are equal, right? This here is minus this, right? T of r. Well, and if you deal with integrals of this sort, what you do is always the same thing. You apply the Gauss theorem. In order to apply the Gauss theorem, I need the divergence under the integral. So I have to write everything under the derivative. So for this, of course, I have to use the product rule. So I write everything under the derivative, tio at t and r xkl. And then I subtract the terms which I've added, right? I have added derivatives of these two terms. So I subtract them now. tio, t of r, di, xk, xl, plus xk, di, xl. And here's a bracket. So the first integral is now a divergence. So I can use the Gauss theorem. And with the Gauss theorem, I get an integral over the boundary of kr, over this expression. Tio, t of r, xkxl. And the volume integral becomes a surface integral. So now I need the surface element. I'd call it dsi. dsi. That's the surface element on this sphere. Yeah? So this integral, this volume integral, is the same as the surface integral by Gauss theorem. And then the remaining terms are what? Plus integral over kr, tio, t of r. And if I differentiate xk with respect to xi, I get a Kronecker, right? So this is Kronecker ki, xl, and then from the other term, Kronecker li dv. And what's this integral? Question to the audience. What is this integral? Our energy momentum tensor is different from 0 only inside the sphere. And I'm on the boundary of the sphere. So this is 0 on the domain of integration, right? Because it's non-zero only inside the sphere. So on the boundary it is equal to 0. So this integral is 0. And I end up with a comparatively nice expression. I end up with, is a minus? No, it's a, yes, it's a plus sign, it's correct. But I think I forgot the c, right? I forgot the c here, yes. So it is c times integral kr tio t of r. Well, I can write it in the following way. The Kronecker makes the I into a k, and then xl. And from the other term, it makes the I into an L and xk. That's the result from the first derivative. Actually, I want to calculate the second derivative. I do it with precisely the same methods. So I get second derivative qkl of t. So I have to differentiate this another time. So I have another time to multiply with c and to apply the derivative d by dx naught under the integral. So I get c squared integral over kr d naught, d by dx naught of the whole expression. Tk naught tr. Well, actually only the t, the energy momentum tensor depends on t, right? This is independent of t. So I can write it outside of the integral, plus do t lo t of r xk. I play the whole game again. So I use again the fact that the divergence vanishes. So I make this into a spatial divergence. So then it becomes minus di tki tr xl. Yeah, I used again this energy conservation law here. And the second term, I need a bracket here, plus di tli t of r xk. And again, I want to use the Gauss theorem. So I write everything under derivative and use a product rule. So then I get di of tki tr xl, everything under the derivative, minus a term which I have added. That's tki di xl. And from this term, I get plus di tli trxk minus tli dixk bracket dv.
This should be T L0. I think here in the last line, the last line in the middle.
That's the last line, is it?
No, in the middle.
This one. Okay. Oh, yes. Thank you. That was nonsense. That I think it's just the writing. No, wait a minute. What did I do here? The I becomes L. Yes, and the 0 remains. Yeah. It was in this way, but the order is irrelevant. Yeah. Okay. Thank you. Yeah. This was just a writing mistake. But I hope this is correct. So we can continue now here. So again, I use the Gauss theorem for this term and for this term, right? So then it becomes minus c square integral over the boundary of kr tki tr xl dsi. And from this term here, I have a minus outside of the bracket, so it's again minus c squared integral over kr tli tr xk dsi. So these are the two terms with the total divergences, and the remaining terms are these two. So they come with minus and another minus sign. So you come with plus c squared integral kr tki t of r delta il plus tli t of r delta ik dv volume element. Okay, and the first two integrals are again 0 by the same argument as before, right? Because t is different from 0 only inside the volume. And that's our final result. So we found the second derivative is what? It is plus c squared integral kr. So here the Kronecker makes the I into an L. So tkl t of r. And here the Kronecker makes the I into a k. So I get, well, I get it with the indices in the other order, but this is symmetric, right? So it's the same thing. So I can just write this is 2c squared integral kr, and then tkl or tlk, whatever you like better. It's the same thing, and that's the result. So the second derivative of the quadrupole moment is given by the integral over the energy momentum tensor. K and L are spatial indices. We are only considering the spatial indices. And now I compare with this expression here. An integral over the energy momentum tensor. That's what enters into our far field expression. Okay, you're still looking at this formula with a surprised look in your face. So any problem with it? So this is just calculation, just differentiating and using the Gauss theorem. That's all we needed. So comparison with the far field expression. For gamma mu nu, that was this formula here. You see that an integral over t mu nu also occurs here. Well, at a different time, at a retarded time. So we have to be careful with the time argument. So if I write this expression here for the spatial indices, so for mu and nu I choose spatial indices k and l, t and r, then this was kappa over 2 pi r integral kr tkl at the retarded time, t minus r over c, r prime, dv prime. Well, if I call the integration variable, of course, I could call r prime here also. Yeah? So if you like, you could write here r prime. You could give any name to the integration variable. And if we compare this with this expression, then we find that this is kappa over 2 pi r. And then I take the 1 over 2c squared to the other side, 1 over 2c squared, and I get the second time derivative of the quadrupole moment, but at the time t minus r over c. Yeah? Not at the time t, but at the retarded time. Well, that's physically quite reasonable, right? What the observer observes at time t cannot be determined by what the source does at time t. Yeah, the signal needs a certain time to travel from the source to the observer. And this is this retardation term which takes care of this. So in this approximation, yeah, this was only an approximate formula, far field approximation, only the leading order term was taken into account. In this approximation, the far field is completely determined by the second derivative of the quadrupole moment. So in particular, the far field is 0 if this derivative is 0. So we need a time-dependent quadrupole moment in order to get a signal in the far field. Yeah? And that's quite analogous to electrodynamics. In electrodynamics, we have the potential AK, for instance, and we have the dipole moment here with only one index. And here, well, the origin of this difference is just in the fact that we have now a quantity with two indices. Here, a second-rank tensor rather than a first-rank tensor, and that's the reason why the quadrupole moment is a relevant thing, not the dipole moment. So a very, very nice source for a gravitational wave would be a squashed sphere, right? That would be the easiest way in order to produce just a time-dependent quadrupole moment. You take a sphere and you squash it rhythmically. This produces a quadrupole moment. But of course, more complicated motions of objects also have, among other things, a quadrupole moment. They have other moments in addition, but they don't matter. So for instance, if you have two stars circling around the common barycenter, then this also has, among other things, a quadrupole moment. It has also all the other moments, but in particular it has such a term, so this could be observed. And that's actually the way in which gravitational waves have been observed, indirectly. There's a source, a binary pulsar, and the quadrupole moment does depend on time, and we observe this in the far field here on Earth. Actually, I deliberately derived the formula for the field itself, for the gammas, for the spatial components of the matrix, which really gives the distance between freely falling objects. We discussed this last time, right? These coefficients, they really have something to do with the distance, the physically measured distance of freely falling objects. So you can measure this quantity far away from the source just by considering how freely falling particles are accelerated relative to each other. And this is related to the quadrupole moment. This formula is mathematically completely unambiguous. There's no doubt about this, what the meaning is, and it's easy to understand. Einstein derived on the basis of this formula a formula for the energy of the wave. That is called Einstein's quadrupole formula. And this is highly debatable because the notion of the energy of a gravitational wave is a very complicated quantity. We have an energy momentum tensor in general relativity which involves everything with the exception of the gravitational field. The gravitational field does not give a contribution to the energy momentum tensor. Everything else is coded in the energy momentum tensor, but gravity is coded in the geometry. In this approximation, in a certain way, you can introduce something like an energy momentum quantity. It's not a tensor actually, it's a so-called pseudo-tensor. You can introduce a quantity that describes the energy and momentum of the electromagnetic wave, but of the gravitational wave, of the gravitational field. But this is a very, very subtle issue because it's a coordinate-dependent quantity and one has to discuss what the real meaning is, and all these problems which arise are still subjects of big debates. So this quadrupole formula, in the form as Einstein derived it in 1918, I think, this is controversial because the meaning of the energy of a gravitational field is a debatable quantity. What is written here is not debatable at all. It's easy to understand, and it demonstrates that the metrical behavior far away from the source is determined in this order by the quadrupole moment. So that gives you a very clear idea of what we need in order to produce a gravitational wave. We need a time-dependent quadrupole moment. And that's what people look for. So they want to observe now this really in terms of the change of length here at Earth with the detectors we briefly talked about yesterday. And this has not been done until now. So until now, what has been done is only it has been observed that binary pulsars lose energy, but this change of length has not been observed yet. So you can understand this on the basis of this formula. And what you should keep away for the rest of your life from this last part of the lecture is that what matters for gravitational waves to leading order is a quadrupole moment, not the dipole moment as it is for electromagnetic waves. Okay. This brings me to the end of the program which I had planned for these lectures. And we have now 1 hour left. And as I announced already last time, I would like to use this in order to talk a little bit about gravitational lensing. Actually, one of you asked me to do this. That was one who is not here today, unfortunately. So he asked me if I could talk about my own research at the end of this lecture, tell you a little bit about what I'm doing myself. And I've been working for many years in gravitational lensing. So I want to give you a brief idea of these things in the last hour now. Talking about gravitational lensing would be rather stupid without pictures. So that's the reason why I want to use a computer for this. So if one of you could reach the... Oh, it comes on automatically, I think. Oh, very good.
Turn off the lights.
Okay. So let's see how this works. Excellent. Okay, so what I'm showing you here are slides from a colloquium talk I gave, I think more or less exactly a year ago here in Bremen, and then later also in Oldenburg. I just translated the slides into English. This was the only work I've done yesterday as a preparation for this. So it is a talk which consists of two parts. In the first part, I talk a little bit about the history of the subject, in particular about the status of observation, so what until now we have really observed in connection with gravitational lensing in the sky. So I want to give you a brief overview of multiple quasars, of Einstein rings, luminous arcs, and some other things which have been observed. So this would actually be a subject for an astronomer, for somebody who's really observing the things, which I'm not. So in my professional capacity, I'm a very, very pure theorist. But nonetheless, I have a certain relation to observational astronomy. I'm a hobby astronomer since many, many years, and I follow quite closely what's going on on the observational side. So I hope I will not talk too much nonsense in this first part. And of course, if you want to know what's going on in gravitational lensing, you should be informed about what's actually on the observational side actually known. So this would be an absolutely necessary background in my view. And in the second part, I talk about one particular theoretical subject, one of the subjects I've been working in. So there are many theoretical issues related to gravitational lensing, which you can investigate partly with fairly sophisticated mathematical methods. And one of these subjects is that you can study the acoustics of light cones. And that's what I want to talk a little bit about. So I will first of all tell you what the definition of acoustic is. I will show you a couple of examples. So I will show you a couple of pictures of light cones, which I think are quite instructive. And then I will review a mathematical theorem which allows to classify actually the stable acoustics. This is based on the theory of differentiable maps, the theory of singularities of differentiable maps by Vladimir Arnold, the famous Russian mathematician who died last year, I think, or 2 years ago. So this will be the subject for this hour. So I hope that then you get a certain idea what's going on in gravitational lensing. And maybe this will whet your appetite to hear a little bit more about this. And then you could come next term to my lecture, where I will give a lecture course on gravitational lensing, which will of course build upon what we have done here before. So if you want to read a little bit about gravitational lensing, there are 2 living reviews. So maybe you've already heard about these. So these are reviews which are regularly updated. So they exist only online, not in a printed version. And the idea is that the author keeps them always live. That's why they're called living reviews, right? So they should be updated regularly. And there's one in this series by Joachim Wamsgans on gravitational lensing in astronomy. So that's more on the observational side and on directly observational related subject. And then there's one by myself, which is more on the theoretical side, of course, and which uses this space-time formalism, which we have been talking about here. So let's begin with the history of the subject. Actually, you might think it begins, of course, with Einstein, right? Einstein invented this gravitational light deflection business. No, it began already earlier, because there was already on the basis of the Newtonian theory, there was debate about light deflection, only by very few people, and not taken seriously by many others. But at least 2 people already around 1800 thought about this. The first was Henry Cavendish in England. He left us only a scribbled note in his in the things he left behind. So it was found only after his death. And it's not quite clear what exactly he did. But from the calculations which we find on this note, it's quite clear that he considered the situation that light consists of particles and is deflected by masses in the same way as other particles are deflected according to the Newtonian theory. And this idea, the same idea, was worked out in a long article with very, very detailed calculations by Johann von Soldner in 1801. And so he wrote quite clearly what situation he wanted to consider. The whole theory is based on Newtonian theory of gravity. And the Newtonian theory of gravity, every particle gets the same acceleration in a gravitational field. Yeah? The acceleration is the same for all particles. The force is proportional to the mass. But if I calculate the acceleration, then the mass drops out, and the mass is the same, the acceleration is the same for all particles. And the idea is maybe that's the same for light particles. Maybe light also consists of particles. This was still a highly debated idea at this time. Also Newton thought of light as consisting of particles. He was a very strong proponent of this corpuscular theory of light. And Cavendish and Soldner were followers of him. So he thought, let's assume light consists of particles, and these particles are accelerated in precisely the same way as all other particles in a gravitational field. So then one of these light particles comes in from infinity. It comes in with a velocity c. That's how c comes into the game in this approach. Yeah, it's the velocity of the light particle at infinity. Now it becomes accelerated by the sun, or whatever the mass may be. So then it becomes faster. It's now faster than, has a higher velocity than c, right? When it is close to the mass. It undergoes a certain deflection by this gravitational attraction, and this deflection can be calculated. Soldner calculated this, and he got this expression in linear order. M is the mass of the deflector, g is of course Newton's gravitational constant, c is the speed of the light particle with which it comes in from infinity, and r is the minimal distance here. Yeah, this is r. And that's the formula which Johann von Soldner derived. And we derived it also in one of the exercises, in one of the problem sheets, right? We followed exactly the argument by Johann von Soldner and derived this formula. And if you insert the values for the sun, the mass of the sun, and the radius of the sun, you get 0.87 arcseconds. So that's what this theory predicts for the light deflection. Now, Einstein comes into the game. This was 1915 when he had found his field equation. He considered the linearized field equation, and in this linearized field equation, he found this formula for the deflection angle. It's the same as Soldner, but with a factor 2, with a factor 4 instead of 2, so it's twice as much. And of course, the whole theory is completely different. In this Einstein theory, there's no attraction by a force produced by this gravitational mass. In the Einstein theory, it is produced by curvature of spacetime. The deflection is produced by curvature of spacetime. So the geometric idea, the physical idea is completely different, but the formula is very, very similar. It's just a factor 2. And well, when this formula was around in 1915 or 1916, then of course the question arose, which one is the correct value? Or maybe is there no deflection at all, right? So when people started to test this formula experimentally, the question was not so much, is there a deflection or is there no deflection? The question among physicists was, to almost to even a stronger degree, was the question: is it the Newtonian value or is it the Einsteinian value? And as you certainly know, I've mentioned this in the lectures, and you probably knew it before. This was tested by Arthur Eddington in 1919 during a sun eclipse expedition. So Eddington, together with 3 colleagues, observed a sun eclipse. Actually, Eddington with 1 colleague observed it in West Africa, and the other 2 colleagues observed it in Brazil. Sobral is in Brazil, Principe is in West Africa. And they took a couple of pictures of the sun during the time when it was eclipsed. So you can, it's hardly recognizable. Here you see very, very dim these marks, which indicate the position of stars. Yeah? And these were compared with the position of the stars in pictures which were taken half a year earlier, when the sun was not in the way. And what you expect from the theory is that the position is pushed radially outwards by either the angle 0.87 arcseconds or or twice as this, 1.70 something arcseconds. And what Eddington observed, the data which he actually then published in the proceedings of the Royal Society, were these here, which are clearly voting in favor of Einstein, right? They are even on the other side of the Einsteinian value. They are even bigger than the Einsteinian value, not half as the Newtonian theory predicted. But I already told you that he produced these results by omitting all data which didn't fit his expectations. So he just sorted out a couple of plates where he said, well, there were ants, they were eating up the photographic plate, so I couldn't use these plates. And he used only the ones which gave the nice results. So if you look at the data more carefully, if other people had done, then it's not so clearly in favor of Einstein. But that's just a historical remark. So this has been done later, for instance, in 1959 by a group of radio astronomers with a very, very high accuracy. So that's a relative error from these 1995 observations, with radio telescopes, of course. Yeah? So in more recent years, one always uses radio telescopes for this observation. First advantage is you don't have to wait for a solar eclipse. And the second advantage is you get a higher resolution. Yeah, you can get angles with much higher accuracy if you use interferometric methods with radio telescopes. So there's no debate nowadays that the Einstein's value is very, very well experimentally established. So light does deflect, gravitational fields do deflect light according to Einstein's formula. And when this observation was done, when in 1919 Eddington reported to the Royal Society in London these results, then there was one person in the audience who raised the question, this was Oliver Lodge, he raised the question, can we say that the sun acts in exactly the same way as a lens? Is this a reasonable way of looking at this matter? So that from then on, the word gravitational lensing was into the game. And well, what this discussion resulted in was it can be viewed as analogous to a lens, but a lens with a very strange shape. Not this ordinary type of lenses which we have in, I don't know, in our specs and things like that, and in telescopes, but a very strangely shaped lens. So if you want to mimic the light deflection according to Einstein's linearized formula, yeah, so what is drawn in the upper picture is light rays coming in from the left horizontally, and they are then bent according to the formula which derives from Einstein's linearized theory. Then we can mimic this deflection precisely by a lens. And the shape of the lens must be given by a log function. Yeah, this is the x-coordinate, this is the y-coordinate. And if you shape the lens according to this formula with a constant k, which is related to the mass m of this object, then you get precisely the same deflection. So you can mimic gravitational lensing according to this linearized theory with a plastic lens of this shape. And actually, there are many colleagues who have done this. So here in Germany, we had Schur-Refstal, who had such a lens, and he traveled through all the lecture halls and demonstrated this in many talks. And so what you would do is you would produce a lens with this shape, and then you would look at objects through this lens, and it would give you precisely the same impression as you would have if you look towards the sun when other light sources are situated behind the sun. So I have never had such a lens, but of course nowadays we don't really. First of all, we have something. Every one of us has something which is very similar to such a lens in his kitchen. Namely, if you look for a wine glass in your kitchen, you will find that with great probability you will find one where the foot has a very similar shape. So if you look through a wine glass, so that the foot is a thing which makes the deflection of the light coming from the other side, then you get an impression which is very similar to what you have in gravitational lensing. Well, it will not have precisely this form with a log function, but something qualitatively very similar. In any case, if you do not have such a lens, of course you can simulate this with a computer. Yeah? And that's what I've done on the next slide. So I have done this with Mathematica. So I calculate the light rays with the help of Mathematica for the situation that I have a light source which has a mass of the sun, which has a distance from us, exactly the same way as the sun, but whose radius is much smaller. So it is a sun strongly compressed, yeah, by a factor 60, I think, or something like that. So the idea is, of course, is that then I get much bigger deflection angles so that one can see something, yeah? Not just this tiny deflection of 1 arcseconds or so, which in this picture nobody could even realize. Yeah? So we have a sun which is condensed now in a much smaller volume, and the object which is lensed is a Saturn, which moves behind the Sun, again with the correct data. So the distance to Saturn and the diameter of Saturn, they are correct. They are the real value. So the only thing which is changed in comparison to the real situation is the radius of the Sun. Yeah, this is made smaller by a factor 60. And now you see what you would see if the Sun would have such a small radius, so that we would get nice lensing effects whenever Saturn moves behind it. So you see, as far as the angle between the Sun and Saturn is fairly big, there's nothing spectacular. Saturn looks as it looks always. But if it comes closer to the Sun, then you see that a second image is formed. Can you see this? It comes about here on the right-hand side of the Sun. Yeah? There's a tiny image, a second image occurring. Oops. We don't have a pointer, do we? Ah, very good. Excellent. Thank you. So here is this little image. Yeah? The second image occurs. And that's easily understood. What happens is, from this image, the light comes more or less directly towards the observer. From this image is formed by light rays starting from the light source and then going behind the deflector, being deflected by a fairly big angle, and then arriving into my eye. So the light from this object and light from light which produces this image and light which produces this image goes on different sides of the deflector. Yeah? And if the angle becomes smaller, if Saturn moves closer to the Sun, then this image becomes bigger and brighter, and both images become more and more distorted. And if the object is precisely behind the center, then we have this famous Einstein ring, which is obvious from symmetry, right? If the object is precisely behind the object, then I have rotational symmetry around the axis, and what I see must be a circle, yeah, or a ring. So that's what we call an Einstein ring, which is historically not quite correct, because actually the first person who predicted the existence of these rings were Qualzon. So one should call them Qualzon rings. He wrote a short paper about this in the mid-20s, but it's usual to call them Einstein rings, which refers, of course, to the fact that the whole theory goes back to Einstein. Well, and if Saturn now moves further away to the other side, then we have the same situation backwards, mirror symmetric, right? So that's what you would see if Saturn moves behind the Sun, and if the Sun would be much denser than it actually is. So that's a theoretical study, right? The Sun has actually a much bigger radius, so we will never see this in the sky. So the question is there maybe any other kind of source for which we can see lensing really in the sky? And this was for many, many years an open question. Einstein wrote one paper on this subject, which was highly pessimistic. He wrote a paper in the mid-60s, where he came to the conclusion that observation of such multiple images or of such rings is practically impossible. And the situation he considered was that a star in our galaxy is lensed by another star. So that's a typical terminology which has now become common. So if the light is deflected by such a gravitational lens, then we say it is lensed. Yeah, that's the terminology. So here's a deflector is a star. The deflector is a star in our galaxy, and the light source is also a star in our galaxy. And Einstein calculated that, well, by all probability, the angle between the two images is so small that one would never observe this. And the probability that the alignment is so perfect that we could observe a ring is practically zero. So this was a highly pessimistic paper. And I think it had a very bad impact on the whole subject, because if the master himself says we will never observe this, and of course other people are not particularly interested in it. So at the same time, there appeared a second paper by this gentleman, Fritz Zwicky. And he considered a different situation. Not a star lensing a star, but a galaxy lensing a galaxy. So here's a deflector as a galaxy far outside of our galaxy. And the light source is another galaxy even farther away from us. And he estimated the probability that one would see multiple galaxies. And he came to the conclusion that this is very likely, that one could observe this. And he was the first to really sit down at the telescope and looked into the sky and searched for double galaxies, binary galaxies. which might be actually only one galaxy from which we see two images. He died in 1974 and he never found anything in all this time, unfortunately. But had he lived 5 years longer, then he would have seen that his prediction actually came true. In 1979, the first double object was observed. It is a double quasar. So what's a quasar? Does everybody know what a quasar is? Well, quasar stands for quasi-stellar radio source. So at least the first observations were made in the radio spectrum. Later quasars were also observed in the optical spectrum. So this is only a historical fact that they are called radio sources. And quasi-stellar refers to the fact that one sees that they are just seen point-like stars. So at least the first observations which were made of them didn't show any structure of them. And the modern interpretation is that these are the nuclei, the small and very compact nuclei of galaxies. So what we observe are actually galaxies, but we don't see the whole galaxy, we only see the nucleus of them, which appear point-like under many circumstances. And well, there are lots of quasars known in 1979. The first ones were observed in the early 60s. So by 1979, there were many quasars. Some of them occurred in pairs. And there was one particular pair where these gentlemen, Dennis Walsh and his collaborators, found very strong evidence for the fact that these are actually not two quasars. It's only one quasar from which we see two images. It is in the constellation Ursa Major. That's what we call in German Großer Wagen, or what the Americans call the Big Dipper. So it's high in the sky here in our latitudes. But unfortunately, the object is very dim. It is 17th magnitude, so that's not observable with a small telescope. So, well, very ambitious hobby astronomers might be able to see them photographically, but certainly not visually. So this goes beyond the capacity of an amateur telescope, at least visually. So, and the distance is 6 arcseconds. So they are 6 arcseconds apart. So as I mentioned already, so my favorite object of comparison is always Jupiter. Jupiter has a diameter of 45 arcseconds. So if you have ever seen Jupiter in a telescope, you have an idea what 45 arcseconds are, and these are 6 arcseconds. So it's a fraction of this. That's a fairly small angle, but that can easily be resolved with a small telescope. So my little telescope can easily do this, but it cannot do this here. The magnitude is too dim. So that was this object which these two gentlemen observed. And what now was the reason that they thought that this actually is only one object? It's only one quasar from which we see two images. Well, there are several indications. The first, what they observed was that the spectra are very, very similar. If you take two quasars, from some catalog, you looked at the spectra, they are completely different. It's like the fingerprint of a person, right? So if you have two spectra from two different quasars, they will look completely different. These two spectra of these two images are very, very similar. So you see this maximum here, this emission line here, you have the same emission line here. They are not perfectly identical, but they are very, very similar. So for instance, you have here an absorption line, which is not here. So they are not completely identical. But this can be easily understood. So the idea is it's actually one object. So the spectrum as it is produced by the light source is precisely the same for both images, because it's the same physical object. And the tiny differences which occur here, they are produced by intervening matter. So the two light rays take different paths. One takes this path and the other takes this path. So there will be different sort of matter in between. And this will produce different absorption lines. So one can understand that they are not completely identical. But the very fact that they are very, very similar indicates that it is actually only one index, only one quasar. Second indication was that, so these are the two images, the two quasar images. The second indication was that, well, when this idea of a gravitational lens was around, then of course the question was, where's the deflector? The mass which actually does the deflection, which is between us and the quasar. So one looked more carefully, and then one found here this dim spot, which wasn't known before these three gentlemen started their investigation. And the idea is that this is the galaxy which makes the lensing, and these are the two images of the distant quasar. And a very strong support for this idea comes from the redshift. If you measure the redshift of these three things, then you see that these two images have precisely the same redshift, namely 1.4. And this thing here has a much smaller redshift. The redshift in cosmology is a measure for the distance. Yeah, the farther away, the bigger the redshift. So these two things, well, what is told by this result that the redshift is the same is that we can exclude the case that these are actually two quasars which have nothing to do with each other, which are just seen accidentally in the same direction. One is close to us and one is farther to us, and they seem to occur close to each other just because they are near a common line of sight. This can be excluded. So if they are two different physical objects, then they are actually really close together in space. Yeah, they have the same distance. And the galaxy has a smaller redshift, so it is between us and the quasar. This fits, of course, perfectly with the idea that it is an object which produces a lensing effect. So these are strong indications. And then there's another indication which I would say is almost a proof that it must be the same object. That comes from the light curves. So if you observe the brightness of the two images, you see that it's not constant. It changes over time. So here is shown in red the time as a light curve for one image and in blue for the other image. It's, the two pictures refer to different spectral ranges. So this is done with different filters, so to speak. So it suffices to look at one of the pictures. So blue is one image, red is the other image. And you see that the light curve, the variation over time of the brightness, is very, very similar for the two things. But the time scales are shifted. So the time axis for the red curve is not the same as the time axis for the blue curve. You see here is December 1905, and here is December 1905 here to the right somewhere. Yeah? So it is shifted by approximately a year, a little bit more than a year, 417 days. Then the two light curves fit one over the other very nicely. And what's the interpretation? Well, the interpretation is it is one object. It goes, there are two different paths of light, and the travel time for the two paths is not the same. So for one of the paths is longer than the other one. So that makes this difference in the travel time. So we can deduce from this observation what's the difference in travel time for the two light rays. And well, this couldn't be a coincidence, right? So this is really you cannot explain this in any other way than by assuming that this is actually only one object from which we see two images. So this is now a very well established double quasar situation, a multiple imaging situations. There are several other ones. So one of the famous examples is this here. It's the so-called Einstein cross. So here you see four images of a distant light source. And the deflector is a big galaxy, which you see, well, I'm not sure if you can see it from the back. Yeah, it is in comparison to these points, it is very, very dim, and it's very, very large. Yeah, so that's a deflector. This big galaxy is a deflector, and these are the four images of the light source, which are behind the center, almost aligned. So the situation is very nicely symmetric. So that's the situation where you have four images. There's some other ones where you have also four images, and there are a few where you have even more than four. I think there's at least one with 5, and I think also one with 6. And yeah, so in this order of magnitude, that's I think the maximum which has been observed so far with these multiple quasars. So these multiple images have been observed now in to a fairly large number. There are many candidates, so we are sure that they really exist in nature. What about the rings? So we expect also rings if we have almost perfect alignment. The first such ring was observed in '88 with a radio telescope. So in the beginning they were called radio rings, but later they were also observed in the optical range. So, well, it's not a perfect ring, but the ring is almost close. So you see the symmetry is not perfect, but it is almost, it results almost in a closed ring. These rings are typically fairly small. So the diameter is typically just 1 arcsecond or something like that. Yeah. This is one example. Here's another, even more famous example. That's a picture which is taken by this instrument. HST is Hubble Space Telescope. Enigmos is the infrared camera. IC stands for infrared camera. So that's a picture in the infrared. And you see fairly nicely the ring which is produced here. And you can compare this with a radio image of the same source. That's what's shown here. So that's a radio image. These level lines give the intensity in the radio spectrum. That was taken with an earthbound telescope, Merlin. So this shows you how the same object occurs in the infrared and in the radio spectrum. So that's another example where you see such a ring which has a diameter, as I said, of approximately 1 arcseconds. So there are a couple of such cases, not very many, but I don't know, a dozen or something like that. So they are also well established now. So these are fairly small things where we have almost close rings. And then there's something which is much bigger. That's the reason why they are called giant luminous arcs. So there we have strong distortion, but there's not a symmetry which would produce really a ring. So we only see an arc. So here they are typically seen in galaxy clusters. So there are many, many cases where you view a galaxy cluster and you see inside this galaxy cluster, you see these arcs. Here's a very big one, and here there are smaller ones if you look more carefully. And the idea is that this is not a gas filament or something like that, as you might think. This is a galaxy. It looks like a galaxy usually looks like, more or less elliptic, roughly. Yeah? And this strong distortion is just produced by the gravitational field of the intervening masses. So just like my Saturn was distorted by the gravitational field of my fictitious sun, in the same way this galaxy is distorted by these intervening masses. And well, by investigating the direction and the strength of this distortion, you can estimate the mass of the galaxy cluster, actually. So that's one of the most important methods by which we get information about the masses of galaxy clusters. So that's a method which has been perfectionized and which is very, very regularly used in order to detect the mass which maybe is not visible, right? What we see as visible objects might not be the whole thing. Actually, we are fairly strongly convinced that it isn't the whole thing, that most of the matter is actually dark, that we cannot see it directly. And the gravitational lens effect gives us an opportunity to observe this. So this began in the mid-80s, and there are now thousands of such arcs which have been observed. So the situation is now, on the observational side, really very well established. So from the present situation, we wouldn't need gravitational lensing as a test of general relativity. Yeah? That's completely settled now. Nobody doubts that general relativity predicts this correctly. So what people nowadays focus on is to use gravitational lensing as a tool in astrophysics, not as a test of general relativity. That's no longer important. We really use it as a tool in order to get some information about the universe. And one possibility is the one I just mentioned, that we can use the gravitational lens effect to detect dark matter in galaxy clusters, for instance. So this has been done for many, many clusters, and the most famous object for which this has been done is shown in this picture. It's a so-called bullet cluster. So that's a picture which was in all newspapers when it occurred, I don't know, 6 or 7 years ago. So this is, I'm sure many of you have seen this before. And that's a very good example of what you can actually do with the gravitational lens effect. So what we see here is 2 galaxy clusters. Here's the center of one galaxy cluster, here's the center of the other one. And there are 3 pictures laid over each other. So one picture is an ordinary picture with an optical telescope. It shows you the galaxies as these spots here. The second picture was taken with an X-ray telescope. This gives these red clouds here. So what do we see with an X-ray telescopes? We see mainly the hot gases in these galaxy clusters. They produce X-rays. So the distribution of the hot gases is given in these 2 shapes for the 2 galaxy clusters. And then we have the blue cloud. The blue cloud is no picture, no photograph, whatever. It is a result of a calculation. It's a result of a lensing calculation where people have evaluated the distortion of background galaxies and from this reconstructed the distribution of the mass density in the cluster. So that's a gravitating mass as it is calculated from lensing. And now you see the interesting thing is the gravitating mass, the blue cloud, coincides very well with the optical picture. Yeah, where the optical picture, where the so to speak, the barycenter of the visible galaxies is, there's also the barycenter of the two blue clouds, to a very good approximation. But the red cloud is very, very much displaced from this. And the idea is that there are two clusters which have collided. One rushed into the other like a bullet. You see here this bullet-like shape. Yeah? And what happened is that this blue stuff, which is shown in blue, which is a gravitating mass, that this went through each other almost without affecting each other. But the red stuff, the hot gases, they collided and then they lagged behind. Yeah? So there are two components of the matter. The hot gases, which really collided and then lagged behind, and this blue stuff, which went through each other almost without affecting it, without any effect. And this is the best direct evidence for the existence of dark matter which we have. Yeah, this blue stuff, this is the dark matter. It's not visible in terms of like the hot gases which really emit electromagnetic radiation. We only see it in terms of its gravitational action. And we see that it is related to the visible matter. So it follows which is visible in this optical picture. So which is given really by the stars in the material, not by the hot gases. So it strongly differs from the distribution of the hot gases. So there's a mysterious component in these galaxy clusters which is not hot gas, which is some other sort of matter. And it must show very little friction with each other because the two blue clouds went through each other almost without any effect. So what we see here is really what we call dark matter. We really see it in this picture. Of course, people who don't believe in dark matter, they try to explain this in a different way. There are theories of this sort. Maybe you have heard about MOND, modified Newtonian dynamics. That's a theory which tries to explain these things without dark matter. But they really have a big trouble in order to explain this picture. They try to do it, but it's very difficult for them to explain this picture. So in my view, this is really a very, very convincing argument that dark matter really exists. We don't know what it is, but we do know that it is there. Yeah? So that's what we observe from galaxy clusters. And another method by which we can observe dark objects goes under the name of microlensing. Microlensing is the situation where we have actually multiple imaging, but the images are so closely together that we cannot resolve them. So we observe the whole effect of the lensing only in terms of the total light curve. So that's the total intensity of the object changes. We cannot resolve individual images. So this can be used, for instance, in order to detect brown dwarfs, for instance, in the halo of our galaxy. So let's assume there's a brown dwarf. That's a dark star, a star which is not bright enough so that it can really be seen in terms of light which is emitted by it. And now let's assume that a star moves behind this dark object. So then the light will be influenced by the gravitational field of this dark object, and this has a focusing effect. So if it is close to the dark object, then the light is strongly focused towards us, and this has the effect that it becomes brighter. And then when it has passed behind the object, then the light intensity goes down again. So that's a typical microlensing curve over time. And this tells us that there's a dark object which produces this focusing effect. So this could be a brown dwarf, for instance, or any other object which is dark. So for instance, it could also be an exoplanet. So with this method, a couple of exoplanets have been observed. So from the, 600 something exoplanets we know by now, only a small portion has been observed with this method. But nonetheless, it is an important tool in this field. And many, many dark objects have been found in the halo of our galaxies. So most people think that this will mostly be brown dwarfs. So such microlensing events are observed by the thousand now. So this is automatized completely. So there are fields in the sky which are observed over time by machines. And when a change in the intensity of one of the images occurs, then a bell rings and astronomers are alerted, and then they run to the telescope and take the light curve. That's roughly how this works. So these are big collaborations of of astronomers who observe these microlensing effects. And as I said, there are thousands of them have been observed by now. Typically, the time scale is a couple of weeks. Yeah? So some of them only a few days. I think the longest one lasts for a couple of months. But most of them are in the order of 2 or 3 weeks, something like that. So they can be very conveniently observed over a couple of nights. And of course, it's an interesting question to deduce from the light curve information about the type of the dark object. So microlensing is a very important method in order to detect dark objects in our neighborhood, in our galaxy, or maybe in a neighboring galaxy. Whereas the preceding method was related with galaxy clusters, so with faraway objects, these distortion effects. So these are two applications of lensing, which are very important tools in astrophysics now in order to detect dark objects. So this was a rough overview of the observational situation. Let me talk a little bit about theoretical issues. So what can you do if you are a theorist? What can you do with gravitational lensing? So you can do actually quite a lot of things. So you can use quite sophisticated theory in order to discuss lensing. So one of the things you could investigate is the geometry of light cones in general relativity. But everything that we see, that an observer sees at a particular instant, think of an astronomer here and now in his observatory. What can he see with his telescopes in the sky? What he can see is what is on his past light cone, what arrives at this event along the whole light cone. All the information about what he can see is coded in the light cone. So the geometry of light cones is very crucial for understanding gravitational lensing. So here's a light cone as it looks in Minkowski spacetime, where we have no gravitational field. Then the light cone is a very smooth, very nice hypersurface. Yeah, here's the observer at one instant of time. So if I consider a whole world line of an observer, then he has a light cone at each instant. Yeah? So it's only at one particular instant of time. That's what this light cone refers to. And if the light cone looks like this here, then every light source, the world line of every light source has precisely one intersection with the light cone. That's the situation in special relativity, when we have no gravitational fields. And then there is no gravitational lensing. There's no multiple imaging. Multiple imaging would require that the world line of the light cone intersects the light cone at least twice. Yeah? Then we would have multiple imaging. And you see it is necessary for this to happen that the light cone develops some funny structure, that it folds over, that it has self-intersections or something like that. And these points where this happens, these are called the caustic points. So, caustic point is a typical terminology of in optics or in astronomy. Some people say focal point is the same thing, and the mathematicians say conjugate points. So if you have taken a course on differential geometry, maybe you are familiar with this notion of conjugate points. It's precisely what a physicist calls a caustic point. And what is it in this situation in geometric terms? Well, the caustic points of the light cones are the points where the light cone fails to be an immersed submanifold, so where it is not smooth. Where something, where it folds over or does something like that. And what sort of folding over is possible, I will demonstrate now in a couple of examples. So we'll see that, so the essential thing, the first thing which you should understand is that you need such folding over in order to have interesting lensing situation. If the light cone does not fold over, then there's no interesting lensing. And now the question is what sort of folding over could occur. So, and I want to demonstrate this by way of 3 examples. So these are light cones. These are pictures of light cones, which I have produced with Mathematica. And they are not just drawn, I don't know, from an artist's point of view or something like that. They're really calculated. I've really calculated, or Mathematica has calculated, the geodesic equation in a certain space-time and then plotted the geodesics. So these are really calculated examples. And the first space-time I considered here is a space-time of a string. So think of a source of the gravitational field, which is a string, a straight string. And what is depicted there is a geometry in a plane perpendicular to the string. So I have 2 space dimensions. They are the horizontal dimensions. And the vertical dimension is time. So time goes from the bottom to the top. That's the string. That's the word line of the string, which in this plane is just a circular disk. Yeah? And so the coordinate which is running upwards is time. It's not the length of the string. And this is the light cone of a certain observation event outside of the string. The string is assumed to be transparent. Yeah? So if I follow the light rays into the past from my observation position, I assume that the light rays pass through the interior of the string. And you see here what happens is a sort of folding over. Here is a caustic formed. Yeah? So what we get here is this a little bit enlarged and without the string shown in the way. So you see here are two things which are called cusp ridges in English. So the two sheets come together with a common tangent. Yeah? So that's what one calls a cusp ridge. And where these two cusp ridges meet, there's what is called a swallowtail. That's a point where it looks a little bit like the tail of a swallow. Yeah? So this is, that's the type of caustic you get in this situation. So here you have two smooth sheets which cross each other transversely. So that's not what you would call a caustic point. That's a transverse intersection. A caustic point is something where the light cone is not a smooth submanifold, where really something like a cusp or something like that is formed. Yeah? So that's a transverse self-intersection. If you have a certain background in differential geometry, you might have heard about the notion of a cut point. So what we have here is not a conjugate point, it's a cut point. But here we have conjugate points. So we have what a physicist calls a caustic point. So that's the first example of what the caustic could look like. It could consist of cusp bridges, and the cusp bridges could come together in a swallowtail. So this picture shows only two spatial dimensions. And one way of bringing the third dimension into the game is by drawing intersections of the light cone with a horizontal time slice. So in the next picture, I've cut my light cone horizontally at different times. So if I do it very close to the vertex, then of course I get a sphere. Yeah? So if I'm very close to the vertex, then the light has just traveled the same distance in all directions, so it forms a sphere. But farther away, if I do this further down, then I get funny distortions, and that's what's shown here in this picture. So that's what one calls the wave fronts. Yeah, these intersections of the light cones with hypersurfaces t equal constants. That's what one calls wave fronts. So close to the vertex, it is just a sphere. I've only shown the lower half so that you can look into it. Yeah, of course, it's a full sphere. So this is close to the vertex. Farther away from the vertex, it becomes bigger. And then, if the wavefront passes through the string, then the caustic is formed. So that's a spatial image of the caustic in this wavefront picture. So you see again, it looks like two cusp bridges coming together in a swallowtail. So here the caustics are cusp bridges and swallowtails. So that's the first example, space-time of a string. Second example is something you know. That's our good old Schwarzschild spacetime. That's the light cone in Schwarzschild spacetime. Again, here one spatial dimension is missing, so I'm in a horizontal plane. Yeah, theta equal pi half. Only this is shown, and the time is running from the bottom to the top. This is a horizon. The horizon is in the plane, it is a sphere. Yeah? And you see what happens to the light. If you follow the light rays, the light like geodesics into the past from the vertex, then, well, it cannot move inside the horizon. This would mean that a light ray, well, the time is running from the bottom to the top, so the future is at the top. So if I follow this from the past to the future, it would mean that a light ray passes through the horizon from the inside to the outside. And this cannot happen, because it is a horizon. That's what you call a horizon. Yeah, such thing is not allowed. So the only possibility for the light rays is they must evade the horizon. They must move around it. And that's what they do. Yeah, they wrap around the horizon, as you can see in this picture. And then they have a self-intersection on the other side of the black hole. Again, I've shown the wavefronts. So I have cut this cone at different level surfaces. And then you get this nice picture. So if you do it close to the vertex, you get a sphere as always. Here's a horizon. Yeah, this sphere is the horizon. If you come close to the horizon, then this front becomes slower and slower and slower, and these parts, they wrap around the horizon. And they have a self-intersection on the other side. And here they form the caustic points. These 2 points are caustics points. So in this case, the caustics are just points in space. The first examples, we had Custbridge and Swallowtail. Here we have just points, something geometrically completely different. So this was the second example. Now the third example. That's a famous light cone. That's a light cone in the field of a gravitational wave. So we have discussed here in the lecture gravitational waves only in terms of the linearized theory. But you can do gravitational waves in the full nonlinear theory. There are a couple of exact solutions, wave-like solutions of gravitational waves, of the gravitational field equation. And for one of these solutions, an exact solution of Einstein's field equation, Roger Penrose had discussed the light cones in 1965 in a famous paper. So he had calculated the geodesics, and his geometric intuition was strong enough in order to translate this into a picture. So he was able to draw a picture of the light cone in this situation. So he drew the past light cone of this event. And you'll see what happens is there's again one spatial dimension missing. So time is running from the bottom to the top, and the other 2 dimensions are spatial. So what happens is there's one light ray, which is just straight, which goes here out to infinity. And all the other light rays in this 2 + 1 dimensional picture are refocused in another point Q. So what the gravitational wave does with light, which is emitted from one point and then moves into the past, is the following. It is refocused in another point in this 2 + 1 dimensional picture. If you take the third spatial dimensions into account, you see that this is not actually a point, it is a line. So it is refocused in a line, not in a point. So this is what Penrose produced from equations. Yeah? He calculated the geodesics and then he translated this into geometry, which at this time really required a lot of geometric intuition and a lot of ability to translate formulas into pictures. Nowadays we have it very easy. We can do this with a computer. At this time there were no sophisticated computer programs which could depict these things. So when I saw this picture, I became interested in checking if it was really correct what Penrose had done in 1965. So I took the same gravitational wave space-time, typed it into Mathematica, and let Mathematica produce a light cone. And that's what you get here. So you see, so Roger was precisely right. Yeah, it's precisely what he had drawn. So here you see the light-like geodesics going into the past and then being refocused into this point. And here's the one geodesic which goes out into the past. So that's how the light cone looks into a gravitational wave. So here you have a focusing effect, a very strong focusing effect. So in this picture, even into a point, and if you take the spatial dimension, which is missing into account, you see it's focused into a line. So that's what is sometimes called astigmatic focusing. Yeah? Stigmatic would mean into a point, and into something more complicated, it's called astigmatic focusing. So if you want to see that this is really not a point but a line, you have to bring the third spatial dimensions into the game. And you can do this again by drawing sections of the light cone, by drawing wavefronts. And in this case, I intersected the light cones with planes under 45 degrees. So I did it slightly before the caustic, exactly at the caustic, and slightly after the caustic. And what you get is this here. So this slightly before the caustic, there the wavefront is a paraboloid. After the caustic, it is such a hyperbolic paraboloid. And at the caustic itself, it is just a line, a parabola. So the caustic in this case is a line. So that's the third case, parabola, which is supposed to mean. So in the first case, we had these Custbridges. In the second case, we had points. Now we have a parabola. So it looks as if more or less anything is possible. Yeah? Any sort of geometry could be possible for a caustic. And actually, that's true. Unless you restrict to a certain subclass of caustics, anything is possible. But there's a clear classification of caustics if you restrict to caustics which are stable in a certain sense. And here in this case, stability should be viewed in the following way. We should require that the caustics do not change their qualitative features, their shapes, if I perturb the metric a little bit. And it's very easy to understand that, for instance, the caustic in Schwarzschild is not stable in this sense. Schwarzschild is perfectly spherically symmetric. If you perturb the spherical symmetry a little bit, you can easily understand that this perfect refocusing in this single point on the other side of the black hole will no longer work. Yeah, the light rays will miss each other a little bit. So the Schwarzschild caustic is very easily understood to be unstable. And the question is, what sort of caustics could be stable? And this question has been clarified completely now. It has been clarified on the basis of a theory which was formulated by this gentleman, Vladimir Arnold, which is detailed in this 2-volume book, which is very, very difficult to read. I spent months of my life with this book, and there were many, many occasions where I was very close to throwing it into the fire, but there's all the information you need is actually in it, but it is very, very difficult to read. And on the basis of this theory, several people have worked out the question of which caustics are stable. The essential idea, which then yielded the results in a very nice way, is due to Rob Lowe, colleague from England, former student of Roger Penrose. So I think he made the most important step in order to answer this question. And we know now precisely what are the stable caustics. There are, well, if I restrict to caustics which are generic in a sense, I'll explain in a minute, then I have only these two things which we know from the string spacetime. The cusps, these are ridges where two sheets come together with a common tangent. And the swallowtails, where two cusp ridges meet in a point. These are the only generic cases. Then there are two more stable cases, which are what I call here instantaneous. And by this I mean the following. You may have a light cone where these things occur and they are also stable. So if you perturb the metric a little bit, they don't change their shape. But they exist only instantaneous in the sense that if you have a whole world line of an observer and you consider the light cone at each instant, then this sort of caustic will occur only at one particular instant. So the caustic will have a different shape before this and a different shape after this. So what happens here is what in the Russian literature is called a perestroika. Yeah, I think also in German and in English this word is well known since the Gorbachev era. I think it just means change, right, in Russian, or transition or something like that. Yeah?
Perestroika?
Yeah, change, yeah. So that's the mathematical terminus which you find in the mathematical literature, in the Arnold papers, for these things which occur at one instant of time. And you have a different shape before this and another shape after this. So before this, you must have something of this sort, and after this, you must again have something of this sort, where you have, if you restrict to stable caustics. But at these perestroikas, you might have one of these two things. They are called pyramid and purse, which are fairly funny names. I'm not sure if you associate this with a pyramid, and certainly you wouldn't associate this with a purse, but that's how it is called. So a pyramid consists of three cusp ridges coming from one side, and three cusp ridges coming from the other side, and they meet head-on. That's what we call a pyramid. And a purse consists of two cusp ridges, one from one side and one from the other side, and they meet head-on. And that's it. Everything else is unstable. So that's a nice application of a fairly sophisticated mathematical theory, where we are really told what sort of objects could occur with relevance to observations in gravitational lensing. So that's one example of these things you could do as a mathematical physicist with lensing. So there are other sophisticated mathematical theory which can be applied. I've worked for many, many years with Morse theory, which is an application of variational principles, and to discuss the minimal and maximal properties of functionals, which in this case refer to the travel time of light rays. Or you could use even cohomology theory, which is a sophisticated theory from differential topology. I've written one paper where I really apply cohomology to gravitational lensing. So it's really a field where sophisticated mathematical methods find a very natural application. And that's, well, if you are a mathematical physicist, if you are interested to apply these sort of mathematical things to things which really exist in nature, then this is a very, very nice playground. And that's why I love this field and why I worked with it for many, many years. Okay, so that's what I wanted to tell you. And then we are right in time to stop. And as I said, if you have become interested in this subject, next term I will give a course on this. And apart from this, that was everything. Thank you for listening.